All right, when we left off yesterday, we were talking about a word problem, which also includes how to figure out displacement of an engine. And then it got me thinking. I told you, the way to answer all word problems was with a ratio. And then I realized, well, that's not necessarily correct because that's more of an if-then is all the ratio. This one won't involve a ratio. But anyway, it's the question is, and this is out of your Q&A, but I made it a little more difficult. So a 6-cylinder engine has a bore of 5 1/8 inch and was bored .010 oversized. It has a stroke of 4 inches. What is the displacement? So what we're talking about is we have to figure out, probably shouldn't even attempt to draw something 3D here, but we have a cylinder, and maybe I shouldn't do that. We have a cylinder. It's going out, and a piston is going up and down inside of the cylinder, and a piston is in here. Piston. We got little rings, and it's going to go up and down 4 inches. And the bore is what? The bore. Well, the bore is a circle. The bore is the same thing as what? Okay, the bore equals the diameter. So when I say it has a 5 1/8 inch bore, that's how far it is across here. It's 5 1/8 inches. But what happened to this bore? There's some more information there. It was bored oversized. It means it's bigger than that. So it's 5 1/8 plus .010. Well, let's make that into a decimal so we can work at it. So what is the decimal, or what is 5 1/8 plus .010?
5.135.
All right, so if you don't know that off the top of your head, it's 5, the ABC1, ABC8 plus .01 equals 5.135. And that's the diameter. All right. Well, we need to figure out, number one, the area of this piston that's going up and down. So the area equals pi times the radius square. Well, what's the radius?
135 divided by 2.
Okay, the radius is 1/2 the diameter. So radius, let me see. Diameter divided by 2 equals the radius. And since bore and diameter are the same, we have to take 5.135 and divide that by 2. So it's area equals pi times 5.135 divided by 2 squared. Now going back to, please excuse my dear Aunt Sally, we have to solve for that. What's the first thing we do? What's the P? I heard one person. P is what?
Parentheses.
Parentheses. We have to solve what's in the parentheses. So it's 5.135 divided by 2. 2.5675. Okay, so it's 2.5675. Now what do we do?
Square root.
Okay, we do exponents. Please excuse exponents. So it's 2.565. Well, it's already sitting in your calculator. All you have to do is hit the x square button. And so that's area equals pi times 6.59 and a bunch of other stuff. Now, I'm just leaving it on my calculator, right? I'm not actually changing it to 6.59. And now I'm going to multiply it times pi. So I just hit the times and then the pi button, which is on the left, third one down, times pi, equals, and so my area equals 20.70950955 and a bunch of other numbers. I want to just round to the nearest tenths position, or let's say hundreds, nearest hundreds position. So area equals what? 7.1. So we're going to round to this place right here. We look over here. That's greater than 5. So it's 7.1. So area equals 20.71 inches squared, or square inches. All right. So that's the first thing you're going to do is you're going to figure out what is the area of this piston. But we're trying to figure out the displacement, how much fluid would be pushed out. So we have to multiply that by what now? By the stroke, by how far that piston's going to go. And how far is that piston going to go?
4 inches.
Going to go 4 inches. So we can multiply that by 4 inches. That's not real hard. It's already sitting in my calculator right now. And if I just leave it like this without rounding, I can just hit times 4 equals, and I get 82.838, so I'll round 834 inches squared. And I will tell you that is going to be A, for answer A on the quiz.
Why is square? This cubic.
Inches square inches. We say square inches.
But why wouldn't it be cubed?
But
Oh, I'm sorry. It is cubed
cubic.
inches. Cubed. Sorry. At this point, it's cubed. Thank you. Didn't ahead of myself.
wait, how do we get cubes?
Because that's the cylinder. So it's the square inches of the surface of the piston times the stroke. Now that becomes the cubed.
Oh, I see.
So that's the volume. So cubic inches, cube. And that would be answer A on the test. So A is going to equal 82.84 cubic inches. And is that the correct answer?
No.
Of course not. That's why I put it on A. Why is it not the correct answer?
Times by 4.
You only have one cylinder.
All right. The question was a 6-cylinder engine. So what did we do? We just figured it out for 1 cylinder. So we have to do what now? Multiply it by 6. And since it's already my calculator, I just times 6 equals 497 cubic inches.
You wouldn't put the 0.04.
What's that?
You wouldn't put the decimal in there?
I just left it in my calculator. I never cleared my calculator. So even though I'm writing 82.84,
Okay.
I never cleared my calculator. So I never actually rounded it all to get this answer.
Okay.
So it's more accurate than stopping and rounding, stop, round, stop, round. Just try and keep it in your calculator all times. So that's pretty close to Continental 520. So answer B would be then 497. And answer B would be hopefully correct.
But we are looking for difference between a regular cylinder and this.
There's no difference. It does not say difference between. A 6-cylinder engine has a bore of 5 1/8, was bored 10 oversized. There's my bore. It has a stroke of 4 inches. How far it travels. What's the displacement?
A displacement.
What is displacement? Sure, total displacement. All right. Want we do that one more time?
Yeah.
Okay. So,
Should do it on our own test. That's it. He still needs to get a problem.
it's 3 3/4, and it has a stroke of 1/2 foot.
Not oversized.
Oh, well, we could bore it over now. What is the total? What is the total displacement? Well, since I made it easier, we don't have to worry about this oversize this time. What do? We take 3 3/4. We have to. What's the first step we want to do? What's that? Find radius. Find radius because we're working on finding the area equals pi times the radius squared. If squared goes there. So what is my radius? Radius equals diameter, or bore,
1.875.
divided by 2. So the radius equals the diameter, which is 3 3/4 inches, divided by 2. So the radius is going to equal, and remember I would do that on a calculator, 3 ABC 4, divided by 2. What'd you guys get? I have 1 and 7/8, but I want to make that into a decimal. So which key do I hit on the calculator? All right, second function, FD. So the radius equals 1.875. So area equals pi times 1.875 squared. I didn't need to put the parentheses, but I did. So we can just do that. 1.875, I hit the x squared times pi equals, and what'd you guys get?
11.04.
11.04. So that's my area. Multiply the area by what?
6 inches.
Why 6? I didn't write 6 up here anywhere.
Because it's half of it.
Half a foot. Yeah, being tricky right there. So times 6 inches. So that's right here. That's 6 inches. So times 6. So times 6. I get 66.26797 and some other numbers. Am I done?
Nope.
Have to multiply it by? 4. Why 4 now?
Because you have 4 cylinder engine.
Because there's 4 cylinders. All right, so times 4 equals 265.07.
Inches cubed, right?
Cubic inches.
That is the same.
Yes.
Do you want us to use the decimal places on these?
Yeah. Well, it's yes, I do. I want you to get as close as you can.
Did you get a worksheet with that?
That was yesterday.
Did you do it again?
I don't have another one for you.
How many more worksheets today?
I should have 2 more. All right, but I had a request to go over a few more word problems. I'm going to make some up here. So an airplane flying a distance, so an airplane,
Hey, Kevin,
yeah?
after this, could we maybe do one more gear one? Just for.
Oh, yeah, yeah. Okay, an airplane flying a distance of 900 miles used 80 gallons of gas. We'll say fuel. How many gallons are needed to fly 3,000 miles? All right, so this is what kind of problem then? How are we going to set it up? What's the word? Proportion or ratio. So something is going to equal something. All right, so we can put miles and gallons and miles and gallons. So the given, how many miles do I have?
900 miles.
900. And how many gallons? 80. Over here I have how many miles? 3,000. And how many gallons? I don't know. There's my x. All right, so we're going to cross multiply. I'll do it this way. So 90 times x is what?
1,000 times 8.
90x. 3,000 times 80 is what?
There's 900.
Oops, thank you. 900x. 3,000 times 80 is what? How much? 240,000. So 240,000 equals 90x.
900.
900x. Oh, man. One of you guys are messed up. All right, so what do I have to do?
Divide by 900.
Did you say divide by 90?
900.
900. Divide both sides by 900. So that's going to cancel out. 900 divided by 900 is 1. So is 90 divided by 90, by the way. And 240,000 divided by 900 equals 266.7 gallons. Yeah.
If you can go a bit, can we just,
Can you? You're gonna ask me if you can do it a different way?
yeah,
We've covered that.
like you can just do.
You can do it any way you want to. I don't care. But I'm going to tell. I'm talking to the people who don't know and they want one way to do it. They want one tool. Right? So if I started in with, well, there's 16 other ways you could do it. I'm going to show you all 16.
Could you do that?
Michelle will actually kill me. She told me that, right?
I will tell.
You will too. He will not. Right.
I'm with you guys. You're scared, Kevin, go to church.
I do actually. So
You're still scared?
I'm not afraid to die. All right. If we have a gear and a gear. So this be my spur gear, and this be my pinion gear. And how many teeth should my spur gear have?
600.
600. This is a gigantic gear. Has 600 teeth, and the pinion then has 20. Has 20 teeth. All right. It is making some noise. All right. Then I need a speed. So speed of.
Knievel, what do we got?
What do you want? Speed of the spur gear here? What's my speed?
1200 RPM.
1200 RPM. Okay. How about 120? So it doesn't get too bad. So that's 120 RPM. So what is it I want to know? What do you think I want to know then?
Speed of the little one.
RPM is
Speed of the little one. Okay, so it's going to be just a ratio. And remember, it's going to go spur, pinion, pinion, spur. All right, that's how I set them up. I remember it's SPSP. It's not teeth RPM. It won't work out. It's got to be spur, pinion, pinion, spur. All right, then from there I can fill it out. So I've got my spur gear. We can say, okay, well then that's 600 teeth. And then if I'm going to do teeth, then what is my
120 RPM.
now it says 120 go here?
Oh, spur pinion, sorry.
It's got to be 20. So teeth is going over here. That's really the hard part, is knowing where to put things. That's why I start with the SPPS. And that kind of, then from there I go, okay, well, the teeth should be on this side and the RPM should be on this side. So what is the RPM of the pinion? I don't know. What is the RPM of the?
120.
It's 120.
God, that thing's moving.
You know it's going to be. All right, so we cross multiply. So we have 20x equals what?
72,000.
All right, 72,000. And so all we have to do now is solve for x, divide both sides by 20. And it's just moving along at a measly 3,600 revolutions per minute. So that's what, 60 revolutions per second?
I have a question.
I figured that's why your hand was up.
Since we're on gears, I think it was in the Q&A. It's about the speed ratios.
Okay.
The question asked, what is the speed ratio of an input gear with 36 teeth meshed with a gear with 20 teeth?
It's 36 over 20.
That's it?
Yeah.
Okay. I was overthinking it.
Yeah. So we can make it real simple. What's
So they're just asking for a ratio,
Yeah,
right?
He's asking for a ratio, so 36 over 20.
Okay.
Does anybody have that one? But it probably isn't going to give it in 36 over 20, is
The
it?
answer is 1.8 to 1.
1.8
Yeah, the answer was 1.8.
to 1. Okay. 36 divided by 20 equals 1.8.
Right, all right. Now I know.
It is. So just divide that, 36 by 20. And then you get the answer.
He does not put L on.
All right.
Answer.
Here's one. The parts department's profit. Profit. So profit. What do you want your profit to be?
25,000.
For parts or for us?
25%. So the profit is 25%. So if I sold a valve for $225, what did the shop pay? Now, in thinking about this, before we do the actual answer, let's do it in something that makes a lot of sense. Let's just put a pin in this for a second, and let's do something we can do in our head. What if the markup was 50%? Okay, and so markup was 50%, and we bought something for $100. So let's say we have a tire, and I buy it for $100. Tire, I buy it for $100. What am I going to sell it for?
$150.
Okay, buy, sell. So I'm going to sell it for $150. But so all you know now is that, okay, this tire, this is secret. So I'm selling it for $150 and my profit is 50%. You want to figure out how much I bought it for. Does it work to multiply 150 times 50%? No, why not?
You'll find 50% of 150.
Because if I figure out 50% of 150, the answer is what?
75.
Did I buy it for $75? No, I didn't. 100. So you can't do it that way. So that's why you can't. And some people ask, why can't I just multiply what you bought it for? Just subtract 50%. Why can't I just do 150 minus 52nd percent equals? Because then your answer is 75. And you can see that when it's a number that you can do in your head real quick. But if it's something different, like the 25% of 225, the answer gets hidden and your brain doesn't quite pick up on it. So you have to do it the right way. So we can set that up as a ratio. What is this ratio going to look like?
225 over 1.
What's that?
225 over 125
225 over 125.
equals X.
You're close.
1.2.
Remember, that's a percent. Okay. Equals, and I want to know what 100% was. So remember, the 225 represents 125% of what I paid the shop. So that's what you're trying to find out. What is 100%? You follow that? So what I paid is 100%. What you paid is, well, you're my friends. I give you a good discount. You come to my shop. All right. So,
Unless you're Ivan.
huh?
Unless you're Ivan.
So I can tell you a story, but not now. All right. So we just now I don't want this in percent because now I just got to deal with percent. So let's just cross out the percent signs and make this 1 and then 1.25. So that's a little easier to work with. So 225 times 1 is
225.
220. Very good. You are quick, man.
I know. I'm like really good at math today.
All right. Equals what? 1.25x. So we're just going to now divide by 1.25 and 225. By the way, 1.25 equals 180. Paid 180. And we can look at the same thing over here just to prove it was right. If I'm selling something for $150 and I had a 50%, that was 150%. Yeah, it was 150%. And you want to know what I bought that tire for. We already know it's 100. What was my 100%? Well, that's 150 times 100 divided by 150, and that's going to work out just right. So, oops, I just had 2 zeros. 150 times 100 equals 150x. Divide both sides by 150, and I'm going to find out that x equals 100. And that means, oh, I bought the tire for 100. I already told you that. We started there. So. You guys are aware of my joke I do with Katie? I say, my daughter is so fast at math. You know, Katie, what's 15,000 divided by 4?
16.
16. See? Told you she's fast. We're going to work on accuracy next. First we'll get the speed, then we'll get the accuracy.
Seriously, dude?
Do I have to take that away from you? I can see that. Yeah.
Nickel pencil.
Okay. All right, time permitting, we'll do some more of that stuff. All right, so you guys have done great. We went through basic math. We did algebra. What comes next?
Geometry.
Well, we did geometry because we did the area, the volume, which is geometry. We'll do that after the break. Trigonomic functions. Trigonomic functions. Now, the reason why we have to deal with trigonomic functions, even though you're not really going to find them in your Q&As on your math portion, you do have to understand them and use them to figure out alternating current, because alternating current is, the formulas for it are based upon trigonomic functions of a triangle. And so I want to get you kind of used to it now, go over it, then in 2 weeks when we do AC, I'm like, okay, I'm a little familiar with this. You can hopefully hear it twice and sort of bring it together. Word trigonometry, it comes from the Greek trigonon, which means 3 angles, and metro, which means measure. So, hey, there you go. All right, so let's see. Let's reference a triangle. So we have a triangle. You may know what a triangle looks like.
I don't. I've never seen one.
All right, there's a triangle. And if I do that little thing, it means this is a 90-degree corner right here. So that little square means it's 90 degrees. 90 degrees. And so we have a 90-degree triangle. I'm going to label this a big letter A and a big letter C and a big letter B. And then this is going to be little c, little a, and little b. I can't wait to see where I'm going with this because I'm not even sure. All right, so each angle has a capital letter. And then across from each angle is a corresponding we'll say side with a lowercase letter. So we have angle C, and across from angle C is A. And across from A we have A, and across from B we have B. And we know that this is 90 degrees right here in this little corner. It's 90 degrees. And that means that we have 2 angles left. And those 2 angles added together would equal what? Those 2 angles are going to be 90. We don't know what they are. If A and B were equal, then they would each be equal 45. So, but they're going to equal something. All 3 of them put together is going to equal 180 degrees. And because this is known, then you can come up with trigonomic functions and ratios to determine exactly what something is. So if I were to know that this is 90 and this is 45 and some certain other information, I could tell you exactly how long it would, the C would be based on a ratio. So that's what we're going to look at. So let's see some other notes here. I need to fit them in where we can take a look at this. We'll put them up here. So A. I don't know if I want to do that. Nah, we'll skip that. All right. And this ratio thing that I'm talking about, I'm going to scroll down a little bit. I wrote in my notes, the side A is opposite from angle A. So little a is opposite of this A. Sometimes referred, no, I don't want to do that. What is C referred to? This line right here. This word sound familiar? Hypotenuse. Hypotenuse. So this is the hypotenuse, this side that's away from the 90 degrees. So that is the hypotenuse. A is sometimes referred to as the opposite. So for reference from A, that's the opposite. This is the adjacent. This is the hypotenuse. If I'm looking at B, this is the adjacent. This is the opposite. And this is still the hypotenuse. So adjacent means next to, opposite across from. Hypotenuse is just the hypotenuse.
Wouldn't the little b be the hypotenuse?
Nope, little b does not become hypotenuse. The hypotenuse is O is C,
No matter what.
no matter what.
It's always across from the right angle, I thought.
It's always, it's what I just said.
I thought you said across from C.
No, it's O is C right here. It's this line here. All right. So again, when I'm referencing A, if I'm standing here at A, standing here at A. This is me standing here. Okay. B is the what? Well, I'll give you some choices.
Is it just the adjacent? It's not the hypotenuse.
Okay, if I'm standing here, B is what?
Adjacent.
Adjacent. A is,
Opposite.
C is.
Hypotenuse.
All right. Since I'm over here, Tim has to be here. So Tim's over here at B. He's not a Martian. A is what?
Adjacent.
B is his,
Opposite.
and C is.
Hypotenuse.
All right.
Mine. It's my hypotenuse.
And if you're over here, which one is the hypotenuse?
C.
C. And it's the opposite. It's opposite hypotenuse. See, it changes when you're over here. All right. So it's always going to be from A or B where we're referencing it. And that is where, and now you have on your calculator, the second row. And what, third or fourth row? Sine, cosine, and tangent. They say going off on a tangent, that's the button you push.
I do that all the time.
And we're going to use those. And I want to simplify this and not confuse people because I can really quick. So sine, cosine, and tangent. Okay, these are ratios comparing two of the sides of the triangle
These are what?
ratios. These are ratios. And it works out like this. So sine of A, angle A, equals opposite divided by hypotenuse. Cosine, I'm just going to abbreviate COS, of A would equal adjacent over hypotenuse. I don't think I need to put A, actually. And tangent equals opposite over adjacent. So if you know 2 bits of information, you can solve for the last bit. And there's a little mnemonic thing where I can never remember it because to me it doesn't sound right, but it's called SOHCAHTOA. SOHCAHTOA. So if I said SOHCAHTOA, like, how do you spell that? Well, I have to look it up. But what it is S is opposite. See, S, opposite hypotenuse. C for cosine, adjacent hypotenuse. And tangent, opposite adjacent. That's an A. And this is where, well, so if you know the angles of the triangle, you can use this formula to figure out the length of the legs. All right? But we're not going to do that. So I'm just going to stop right there and say, that's what that is. Now you know. What do you need to know? Well, when we're working with electricity, and don't freak out on me here.
I'll try not to.
All right, we're going to come back around this. Remember, this is this little part right here. Okay, I know it's not on this part's not on the test tomorrow, but we have to. But it's going to be in 2 weeks. All right, so you can just maybe relax and learn it, and then in 2 weeks. When we talk about DC current, DC comes from a battery, and if I look at the current flow, it is just straight. It doesn't change. But when I look at the stuff that comes out of the wall, for an example, it is alternating current. It goes high, goes through a zero line, and goes backwards. So it actually comes out of the wall and goes back in. It comes out of the wall and goes back in. All right, so it alternates back and forth. So there's a thing called an oscilloscope, and oscilloscope's usually green, so I'll pick green. So if I'm looking at an oscilloscope picture, and this is the zero line, and I say, oh, I hook up a battery to, and it's 12 volts. That 12-volt battery, I'm going to look at it, just going to go like that, just straight across, but straight. I can't draw straight on my pad. And if I said, and I'll just use red to be different, if I said, okay, there's the voltage. Well, if I were to look at the amperage on a oscilloscope, and you guys will use this oscilloscope later, it would just still be the same thing. It would just come straight across, and the amperage would be just there. It doesn't move, right? And that's DC, so that's amperage. But if I was going to look at AC, and here's the zero line, it would go up and down. I would say, well, there's the voltage going up and down. Sorry, it's harder than you think to draw on this thing. All right, so it goes up and down. And I would say, okay, well, there's the voltage of the AC. Be a different color. We'll go black. And then, so if I was going to look at the amperage, well, the amperage isn't as much. In theory, it would kind of go not quite as much, not quite as much, not quite as much, and it would follow this. But it doesn't always follow. You can actually get into a situation where right here my amperage peaked, and right here my voltage peaked, and right here it peaked, and I tried to draw that over here but did a bad job. It doesn't always do that. Sometimes those sine waves start to spread out. And when the voltage is peaking, maybe the amperage is just starting. And so if they don't go up and down together, it's called out of phase. And you want them to be in phase. The more in phase they are, the better, more, what's the word I need? Somebody help me out. Efficiency, thank you, is the exact word, is the more efficient they are. You get out of phase and they're inefficient. And what causes these phase shifts are actually inductors, which you guys know. What is an inductor? The what? It's a coil of wire. All right, where do we use coil? Where do you find coils of wires? So we're talking about SMUD now. SMUD is, they're PG&E, they're putting out all this power, and they need to make sure that these waveforms are in phase. And so where am I going to find inductors?
Transformers?
Transformers, absolutely, is a great one. They come off the line. The first thing they hit is a transformer. Okay, so transformer is going to throw them out of phase. Gets to your house. What do we have in
Breaker blocks.
Okay, it goes to the breakers. Breakers are just breakers. They're just switches. Then it goes into the house. Well, what are we running? Well, you got a blender, and you got a vacuum cleaner, and you've got a fan running, and you got an air conditioning running, and every single one of those things has a motor. And what's inside motors? Coils of wire.
And relays.
And what?
Relays is an inductor inside the relay.
The what? Relays. Okay, yeah, and relays. So inductors do a lot of work. So you have all these inductors. So what's it going to do? It's going to throw it out of phase. So my father-in-law worked for SMUD, and he said they actually have gigantic buildings that are dedicated to bring it back in phase. Well, if an inductor throws it out of phase, we need something to do the opposite of an inductor, and the opposite is a capacitor. So they would have big capacitors they bring online, and it shifts it the other way. So inductor is going to shift these two things one way, and capacitors go back the other way. So if you were working on, let's say, an aircraft, and you have to design, you're going to add something. I'm going to add this motor to this AC system. Well, then you would have to potentially figure out, okay, what kind of phase shift is it going to do? And so that's kind of where we get into AC, is we evaluate circuits and determine what happened to them, if they're in phase or out of phase.
So you're talking about phase as in the voltage versus the amps?
Yes.
Okay.
Yep. This chart that I have, where this is the amps and this is the volts, they start to spread out.
Okay.
So the peak here is not the peak here. All right. So yeah.
So we would, the way we would see, or if it came out of phase, would be the amperage would be different voltage.
Not different at a different period, and I'll show you this when we get there. But I want you to know why you need to know this. All right, not just you need to know it. All right. So given this, you don't see this on an oscilloscope per se. You can do it mathematically. Now, mathematically, when you're working with AC, we just have resistance in DC, which we've all covered in 309. But to plot an AC core, I'm going to look at something like this, where this line right here is the resistance, this one right here. And up here, I would put inductance, and that's my coil, so I'll just put a coil. And down here would be capacitance, and I'll just put a capacitor. And all three of these things work in conjunction to what we call impedance, which is the total sum of all of these things. So you have resistance, which comes from resistors, and you have a like resistance that comes from inductors, and you have something like resistance, but it's not, out of capacitors. And you plot all of this, and you'd say, okay, I have this much resistance, and if I have this much capacitance and this much inductance, you subtract the two, and just visually speaking, would I have more coil or more capacitor? Which I have more of in my little plot here? I have more coil. So you subtract the two and you say, okay, so that becomes right there. So let's say that's my inductive reactances right there. So here's how much resistance I have, here's how much inductive reactance I have, and then you end up say, oh, well, here's my impedance. Well, I missed the line there because it's harder to do than you think. Here's my impedance. So what did I end up drawing?
Triangle.
A right triangle. So if I know what my resistance is, I have, X number of ohms, and it's given, and and you figure out your inductive over here, and you have, well, I have this much inductance, and this is a known quantity. All you have to do is figure out this right here. And so this is an X inductance, and so you figure that out. Well, to figure that out, I just made a triangle, right? So there's a formula. If you know this leg and you know that leg, then you know how to figure out. And what is this called again? Hypotenuse. Okay. And we'll talk about that. Then all I care about is this little angle right here. Because if I had the perfect amount of capacitance to match perfectly my inductance, then those two things would fall right here, if you understand that. So if I had a lot of inductance, whoa, more inductance I add, the worse it's getting out of phase, right? I need to bring in some capacitors. So if I had inductance all the way up to here, how much I would add capacitance until this got to where?
There.
Right here? You're right. Add capacitance until I got to there. And so if my inductance and my capacitance were equal and I plotted it, then that hypotenuse line would be right along here. And guess what? That's perfectly in alignment. So the more this opens up, the worse it's getting. You follow that?
No.
No. I don't think
Not at all.
So you want the angle to
Okay.
be here
I
again.
think a large
Huh?
portion-
What?
I think a lot of us aren't really getting it on this right now.
It's fine.
I'm just speaking up
We're not covering AC right now. So if I teach it to you to a level that you understood it completely, I'm going to go over it again. All right. But I'm teaching you why you need to know this. So, yeah.
So that little angle right above the R, that would be the phase angle?
Yep, this is the phase angle. Or called angle of theta to be exact. So this is the phase angle. So I'm just telling you, in an AC circuit, the more this angle opens up, the worse it gets. And we need to figure this out. Thus the need to know trigonomic functions. So in a triangle like this, if I want to figure out this right here, which is the hypotenuse, there's a formula. What is that formula? You got it. A squared plus b squared equals c squared, where this is A, this is B, and this is C. Well, just for an example, and it doesn't work like this in electricity, but let's just say we had a triangle. And I said this is, and drawing's not to scale, this is 7 inches and 9 inches. What is my hypotenuse? What is my hypotenuse? And this is, and you will be doing something just like this. I will be saying something like you have 9 ohms and inductive reactance is 7. What is my impedance? Well, so then it would be 7 squared. Now, it doesn't matter if I do 9 squared or 7 squared. The A and the B is irrelevant. It's just leg versus leg. A squared plus 9 squared equals C squared. All right, so 7 squared is what?
49.
Plus
81.
81 equals C squared. All right, so 49 and 81 is? 130. 130 equals C squared. Now, here's the problem. Can I just leave that as C squared?
No.
That's like saying 35x. We can't just leave 35x. We got to have just x. I have to have just C. So how am I going to get rid of that square? The square root. So if I do the square root of here, what I got to do to this side? I got to do the square root. You would guess the same thing, you'd be right. All right, so the square root of anything that's been squared is just C. All right, that gets rid of that. So because you remember, if I had, well, I want to make it confusing. Okay, and then the square root of 130, I just put 130, the square root, and I get 11.4. So that means that if this is 7 inches and this is 9 inches, x right there has to be 11.4. Yes?
What does the x mean, like in that graph? Like what would that length?
This right here, this x.
Well, in your graph earlier, like up
Here?
Or I mean, yeah.
Impedance.
So that's a value.
That's a value. That means it's like saying the total sum of the resistance. Because there's different types of resistance. So it's taking all the types of resistance and saying that's what it feels like to this circuit.
Okay.
And that's only for AC. You don't get this in DC circuits. All right, everybody follow that so far? Okay, so that's called, what is this called, by the way? Who invented it? Pythagorean's theorem. All right. Some guy, Pythagorean.
According to Phil, some old white dead guy.
Yeah.
All right, that brings us up to our break time. I hope I didn't break you.
Did you press the record button on this?
I don't believe I did. Yay! You got to ask me that before the end of the lecture.